This conference will now be recorded.
So, very good evening. Today we'll learn how to experimentally determine the gravitational constant. So, we have already learned the universal gravitational law. So, if you remember, the law was given by, so since it is an attractive force, so it is written as minus. So, G, suppose a capital M and small m, two masses are separated by distance r, then it is given by, so this is the mathematical form of the universal gravitational law, gmm by r square. Generally we read in this way. So this g is actually called universal gravitational constant, and it is really a constant. It has a constant value that day we had discussed this, 6.67 into 10 to the power minus 11, and it is Newton meter square per kg square. This is the value in SI unit. So we have read this thing already, but how do we calculate this value of G experimentally? So this great job was done by English scientist Cavendish. So this great job was done by Cavendish. So let us see what was the experiment, how the experimental arrangement and all those things were done, and how do we calculate this G using this experiment. So according to the experimental arrangement of Cavendish, he used two identical lead sphere, small lead sphere, very small lead spheres, and those were connected at the ends of a bar, connected at the ends of a rigid bar AB. So this AB is a rigid bar, okay, and this arrangement, like it was like this to form a dumbbell shape. This is AB bar, and these are two small sphere made of lead, and the masses, they are identical, okay. This lead spheres are identical and their masses are suppose small m. Okay, small m. And this dumbbell or this arrangement was actually suspended by a rigid and inextensible extensible wire, fine wire. Okay, this is fine wire, and this wire is actually made of quartz fibers. Okay, made of quartz fibers. So I'll just repeat this arrangement itself. So Cavendish took two identical lead spheres of same mass, small m. They were attached to or connected to the two ends of a rigid bar AB, and that bar was suspended by a rigid and inextensible fine wire made of quartz fibers. Okay, this was the thing. So these things you have to remember. I'll just remove all the writing part and show you here. Then what happens after keeping this, like after suspending this bar, he took, so third point is that he took another pair pairs of spheres. These are actually big spheres, comparatively bigger. See, these are the spheres S1 and S2, S1 and S2. So big spheres, they are S1 and S2, S2. And how about their mass? Suppose their mass is m, okay, of mass m, masses m, and they were actually kept near to the small spheres, near to the small spheres, but in the opposite direction. Since S1 was kept here near A and S2 was kept near B, but in the opposite direction. See, this was the direction. So this is S1 and this is S2. So this is the way. You can do it either way also. You can keep your S1 here and S2 here. The result will be the same. So look, you have small spheres and then you kept one big sphere of capital mass, like a mass of capital M. Okay, so as you know, these two masses will be, see, A and S1. They will actually exert a force, like they will attract each other by a gravitational force, right? So since actually they will exert force equal in magnitude, the force A is exerting on S1 will be the same in magnitude, but the acceleration produced in A will be greater than S1. So that's why it will have a kind of force in this way, you can think, okay, attractive force in this way. At the same time, this B will be actually attracted towards this, okay. So this is how you look. There are two parallel and equal and opposite forces. Since this S1, S2 are identical, and A and B, these small spheres are also identical. So that's why these forces, see, both will be F. Okay, both will be F. If I say FA equal to FB, but with the opposite sign. So these two parallel forces will form a couple. We have learned already what is called couple. Equal and opposite forces which are not acting, equal and opposite forces, but their line of action of forces are not equal. So they are called actually couple. So look, this bar will experience a couple, and what couple does, couple will not give any resultant force. So no resultant force will be there due to the couple, okay? No resultant force. Then what will happen? As we have learnt already, this bar will experience a torque. What is torque? The moment of the force of any one force of this couple multiplied by the perpendicular distance between the two forces is called torque. So see, F is one of the force of the couple. Okay, if I take F and suppose this bar is of length L, then F into L, this will be a torque. Okay, F into L, if you write in terms of vector, this will be the case, or if you take magnitude, then FL. So this is the torque which will be experienced by this bar. And we know linear force creates a motion or translational motion, and torque creates a rotational motion. So in this case, we'll be seeing that this AB bar will experience a torque, will experience a torque, okay, a torque which will try to rotate it, okay, rotate the bar. And see, it is not a free bar, it is also suspended by a fine wire. That means what? It cannot rotate, like it cannot rotate up to a infinite extent, or maybe to very large extent. In fact, I want to mean that since it is suspended by this fine wire, this rotation of the bar AB will be happening till the torque, see the torque, so this rotation or deflection, I can say, rotation of the bar will be till the time when the torque on this fine wire is not becoming equal to the torque due to this gravitational force. So I'll clean this maybe. So I wanted to mean that this torque on the fine wire will give a restoring torque. Until this restoring torque, suppose this I'll write restoring torque on the fine wire is less than the torque on the bar AB, so it will rotate, okay, at the point where this restoring torque will be equal to the torque on this bar, then the rotation or deflection will stop, okay. So this will be called as rotational equilibrium. So this stage is called rotational equilibrium, okay. So I'll just repeat, due to this gravitational force between the small lead spheres and the bigger sphere S1 and S2, there will be a couple which will form a torque, and that torque will try to rotate the bar AB and it will rotate until the restoring torque is not becoming equal to the torque, gravitational torque. Okay, so at the rotational equilibrium, at rotational equilibrium, we can write the restoring torque. This is on actually in the wire, fine wire, and this is in the bar. We can even denote this as restoring torque and this as gravitational torque, and this is restoring torque. Okay, this way also we can denote. So see the torque which is happening here due to twist in the wire. Torque, restoring torque is actually happening due to twist. Twist means, you know, like it will be twisted. Since this point is fixed, this point is rotating, so there will be a twist. So it will be twisted by certain angle, suppose theta. So this restoring torque will be proportional to the twist angle. This is called torsional torque also. Torque due to torsion. Okay, so this torque is actually happening due to the twist. Suppose it was here like that and twisted by certain angle theta like this. Okay, twisted by certain angle theta. So then this will try to bring it back, like this bar this torque will try to restore the bar to its original position. All right, so this torque will be proportional to that angle of twist. So restoring torque will be directly proportional to the angle of twist. So we can write this restoring torque or torsional torque also, we can say. This kind of things we have learned already in case of galvanometer, if you remember. So this restoring torque can be written as K into theta. So this is called torsional constant or twist per unit torque. Okay. We can say torque per unit twist angle. So this is called torsional torque. Torsional constant. It is called torsional constant or torque per unit twist. Torque per unit twist angle. Unit angle of twist. Angle of twist. Okay. So now we know what is the gravitational force between these two. Then we can find out what is the torque, gravitational torque. I write G, gravitational torque, T G or T grav, gravitational torque. So we know F into L, FL. So what is F here? Minus G into capital M of the sphere S1. We can take any one. Okay, both are identical, so it will be G, and this is small r. This is the distance between the centers of the small sphere and capital sphere. So this is the distance r. Okay, now if we at the rotational equilibrium, we can equate these two and then we can find out the value of G. Let me write it. So K theta we can write equal to minus G. I can take this force as like magnitude of the force, so I'm just removing the minus sign by r square. Okay, now from here G can be written as K into theta into r square divided by m, small m, and capital M. So look, these m masses we can choose. So these are known. Now this distance where I want to keep, that also known. So see, these three things are known already. How to find out this? We can find out this torsional constant by applying an equal amount of I wrote this torque, restoring torque, to be k theta. So this k I have to find out. Sometime for a particular material you will be able to get from the database this torsional constant, or you can find it out also. If you apply certain torque for a known torque, you can find out what is the angle of twist. So just by knowing this torque divided by theta. So if you do this, this is also a simple experiment you can do. You can just apply a known amount of torque, okay, and find out the angle of twist. So knowing this, you can find out what is the torsional constant. Okay. So if you know the torsional constant, but now the question is how to measure the angle theta, twist angle. So there is a nice way to find out the angle of twist. So there will be sometime, a mirror over here, and the light will be given from front on this small mirror attached to this wire. So as the wire rotates or getting twist, the reflected light also will be deflecting. So from the, like, there will be an arrangement of scale on which the reflection of light will be moving. Okay, so that will be an angular scale. We can find out, see, if you have, see, this is the deflection of the light. Earlier, suppose here was the reflection you get from the mirror. So you know this, if you know this length, suppose this is r, so this is theta, and this is the arc length. So s by r is equal to theta. So by doing this, you can find out what is theta. Okay, so just by seeing the reflection on the linear scale, on the linear scale. So I hope you are understanding. If we attach a small mirror with this wire, fine wire, as it rotates, the wire, this mirror also will be rotating. So if you start, like, if you just give a light from front, so you will see the image of the light, or reflection of the light, somewhere here in the beginning. But as it gets twisted, the wire gets twisted, the reflection will no longer be here. It will be deflected to somewhere here. And if you know this length, linear length from here to here, and if you know the distance between this source of light and this mirror, or so this perpendicular distance, then you can find out what is the angle. So by doing that, you can find out the angle also. So experimentally, you can find out what is this theta. Then you know what is k for a particular material, the torsional constant. You know these masses you have chosen by yourself. This r you can choose at what distance you can keep, like you want to keep. So by knowing all the parameters on the right hand side, we can easily find out what is the value of G, capital G, or universal gravitational constant. And this experiment was done by British physicist Cavendish. So that's why, okay, we'll see sometime from this. By knowing this, see, if we know this G, we can find out the mass of the earth also. We'll look in the next section when we discuss gravitational constant. So we'll see how we can even estimate the mass of earth if we know the value of capital G. Now we'll be discussing about acceleration due to gravity. We have already used the value of acceleration due to gravity, some places 9.8 meter per second square, and sometime for the sake of calculation we have taken, for the convenience of calculation we have taken 10 meter per second square. So now we'll see what is the mathematical expression for this G, gravitational, like acceleration due to gravity on the earth surface, and we'll see how this G vary with the depth and with the altitude or height from the earth. So we have already have this experience that if we go higher and higher altitude at the like higher and higher in the mountain, we see the gravitational constant, like value of the gravitational constant is less. That's why we feel ourselves less, like having less weight. Okay, and as you go inside the earth, also in the mining region, in the mines, so there also gravitational constant is having value lesser than this 9.8 or 10. So how mathematically, see, suppose there is given this 10 meter away from the earth surface, so what will be the gravitational constant? Or if it is under the surface, 10 meter under the below the surface, then what will be the value of the gravitational acceleration due to gravity? So those values you will be able to calculate if you know the mathematical formulation, okay, or mathematical formula. So far we know the value only, but now we'll learn mathematical formula for finding out the acceleration due to gravity at any height or any depth from the earth surface. So before we learn that, let me tell you how to calculate the acceleration due to gravity on the earth surface or anywhere inside the earth surface or inside the earth. So first of all, see, earth can be imagined to be made up of a large number of concentric spherical cells, as you can see from here. So you can think that earth is actually made up of a large number of concentric cells, spherical cells. So what is spherical cells? Spherical cells means, spherical cells you can see from here. It is, see, it has, see, suppose this one has 1, 2, 3 cells. Okay, 3 cells having radius A, radius B, and radius C. Cells means like, so this is actually 3-dimensional object. Suppose if you take an onion, a very simple example, maybe we can get many other examples as well. Take an onion, or maybe you can take a cabbage. So cabbage is actually made up of many leaves, right? You can think those one layer, like each layer you can think of spherical cells. In case of onion also we see, right, there is a like covering layer by layer. So you can think those, so those actually coverings has certain thickness. So that's why they are not like, not a thin one, they have certain thickness also, right? Not very thin. So those are actually called spherical cells. Okay, concentric spherical cells. So you see this here. Okay, see this cell, this particular cell has certain thickness. This particular cell also has certain thickness. So earth can be made up of, like considered to be made up of such cells, concentric cells, and the outermost cells is actually at the surface. Okay, or the largest cell is at the surface of the sphere. Okay, and the smallest cell is at the center. Okay, is at the center of the sphere. So actually earth can be considered to be a sphere which is made up of a large number of concentric cells. Okay, fine. Now now if we want to calculate the gravitational force at any point P which is outside the earth itself, so this is the earth. So if we calculate, suppose this has some mass m, small m, and this earth has mass capital ME, or I will write for the sake of our convenience simply capital M. So if we want to calculate, suppose this distance is from this center, this distance is some small r, and this earth has a radius of capital R. Okay, so radius, this is earth's radius, radius of earth, radius of the earth, and capital M is the mass of the earth. Okay, now see, this small r is greater than capital R. So in such case, what will be the gravitational force? Gravitational force will be given by G m small m by r square. What does this mean? This means that, see, this r is the distance from where? This is from center. But see, there are cells which is distance less than r or greater than, see, this is r, this is one cell, this is another cell. So what we are considering, the distance from the center to center distance we are considering. That means we are not considering this sphere or the earth any longer a sphere having such dimension. We are thinking that the earth is collapsed to a point mass having, so it collapsed to a point having total mass m. So by this expression, what is like implied here is that the earth, like the total mass of the earth, total mass of the earth is concentrated at the center. Okay, so this thing we have seen even in case of electrostatics also. So this is called shell theorem. We will have another extreme also. So this is actually outside. So this point mass was outside the sphere. Now, so in this case, we think that the whole mass of the earth as if concentrated at the point where at the center. That's how this distance we are considering in the force equation of force. Okay, always we will take the magnitude, so we'll just remove this positive a negative sign. So this is the case when the point is outside. I'll just write it here somewhere. So the force will be, I'll take the magnitude, so G capital M small m by r square. This is the r and this is the capital R, radius of the earth. Now I take another case. See, now this point P has moved inside. It is being moved inside the earth. See, earth surface is here. Now it has been moved here and it has mass as I had taken here, small mass. This is P outside. But now the point R. See, now the distance R is actually, so here in this figure it is RE. So let us take this also as RE to keep it coherent. So this point mass M is inside the earth. That means small r is less than the RE, that is the radius of the earth. So in this case, you look, there are cells outside. So this particular cell is outside R, outside, and cells having radius cells, so 2 points are there. One point is cells are outside, they are outside. Outside means having radius greater than having radius greater than r, and there are cells having radii are less than small r also. That means you have cells maybe here, okay, here, like that. There are cells inside also. So what does this mean now? See, according to the previous formula what we have already learned, in this case we had taken that mass is concentrated at this point, but can we take that now here and then we can just write as we have written here? No, we cannot. According to the law of gravitation, universal law of gravitation, there is a law called cell theorem. According to cell theorem, the cell outside does not exert force, does not exert force, okay, does not exert force. Then the force will be experienced, so gravitational attraction will be experienced by this mass only due to the cells which are having radii within this small r or below small r. So this will exert a force, but this will not exert force. The cells outside will not exert any force, whereas cells inside will exert force on this point mass, okay. So if this is the case, look now, I had considered the mass of the earth to be capital M, but if I write down the gravitational force, then G, can I write this as M again? No, these cells are already out from the picture, so then I have to write M prime. I have a new mass, so new mass for this particular radius, you can see that, okay. So if I say this has radius of some, so this is actually r, having radius r, right? This is the radius smaller. So I have to find out the mass of the earth which is which is there in this particular radius, okay, and that mass will be concentrated here at the center, okay, that particular mass. So see this shaded region, so this part of the earth will exert a force on this particular point, okay. So the radius will be smaller and that particular part of the earth will be actually applying gravitational force, okay. So we have to write M prime, which we have to calculate, and that is different than the original mass. In fact, this M prime will be less than capital M, okay. So this is the force now, r square is r square. So this r and this r is different actually, so I can take this as r1, maybe this is r2, so that there is no confusion, okay. So here this r, maybe let us take r2, okay. Okay, so now we have to find out the M prime. Anyway, so r and r prime whatever we can get it, but what is the mass? So to know the mass, see, if rho is the density, uniform density, uniform density of the earth. Uniform density means density of the earth is same everywhere, and radius of the earth, like this is the radius of the earth RE. Then the total mass M can be written as volume into density. So 4 by 3 pi r cube into rho. This is the original mass. So what is the mass now? M prime will be 4 by 3 pi small r cube into rho. This is the mass now. Okay. Now if you want, you can substitute this rho in terms of capital mass. We'll just show it here. Okay. Look, then I can get the force G. This mass I'll write 4 by 3 pi small r cube into rho small m as it is, and then it is r square. So look, this G 4 by 3 pi and small r rho, okay, and this is m, and r square r cube that has been cancelled. So look, this rho, if I just substitute the rho will be m into this. Look, I'll write, okay, so in place of rho I'll write rho will be 3 by 4 pi divided by r cube into capital M, the small m, and there was already small r, this small r. I have just replaced the value of rho from this particular equation. Okay, in terms of capital M, the mass of the earth itself I want to write. So look, I'll just write it here, simplify it and write here. So it will be G, see 4 by 3, this will be cancelled, so you will be getting over here just a minute. So if we do that, what we get here, look, what we get is this. Excuse me, there is some problem here. Okay, let me get it here. Okay, just a minute. Okay, I'll write. So what we get, the force ultimately, see G capital M, and then you get small m, then you get this r divided by r cube. Okay, this is the thing you get. Okay, so this is the force at any point inside. So I'll just write it here. So this is the force inside the earth. If you take any object inside the earth, so this is the gravitational force experienced by m inside the earth, okay. Now from this expression we'll be able to get one nice expression. Look, if so Then what is the so force at surface? What is the force at surface or gravitational force at the surface? So gravitational force at the surface will be given by GMM. This R surface means Earth surface. Let us write this as RE. So this also, so when at the surface means small r is equal to RE. Okay, and this you have R cube. So this one will go. So you will have here 2. So look at the surface. I'll just remove this. So gravitational force at the surface will be G mm by r square. Now look, if we apply Newton's second law here, Newton's second law. So let me index this with F inside, and this is at surface. This is the so when we have M at Earth surface, see the force, this mass will be experiencing, that is mass into acceleration, and that acceleration due to gravity. Okay, so this force will be exactly equal to the force at the surface, which we have already got. Okay, so then this can be written as G is equal to F surface by small m. Look, what is the force at the surface, gravitational force at the surface? This one. So if we just remove the mass, then we'll get, so you just divide this and you get the G. So what is the G you get then? So gravitational force divided by the mass of that object, so you get Gm by r e square. Re is the radius of the earth surface, sorry, earth. Okay, so finally what we have calculated is the acceleration due to gravity inside, like on the earth surface. Even inside also, no, inside we may not be able to, because on the earth surface we know the weight of the object, so this we know. So that's how we can find out the gravitational at the earth surface. Okay, let us write this as surface. Okay, or we can just keep this as simply G, small g. Small g we are denoting at the as the acceleration due to gravity on the earth surface. So what we have got, Gm by re square. Okay, Gm by r square. So this is the acceleration due to gravity on the earth surface. Okay, so I think I'll just take another 5 minutes to discuss this thing, variation of the acceleration due to gravity with altitude and with depth. With this I think I have 2 transparencies more. So let us see variation of acceleration due to gravity, like acceleration due to gravity with altitude. That means variation of variation of g with height. Okay, so let us first write the value we know on the surface. So this is g is equal to, suppose here I have taken as r, let it be there as r only. So like radius of the earth is r and mass is capital M only, so Gm by r square. So this is the acceleration due to gravity on the earth surface. Now look, I have kept a mass, small mass, at the height h from the earth surface. So what we can write? See, the center to center distance will be r plus h. So this is the distance we require for calculating the gravitational force. So let us say gravitational force will be then G m m by r square means r plus h whole square. Okay, so from here itself we can write that G can be written as, then G can be written as, G can be written, see, if we know at the earth surface this is the one, so we can write this as G capital M by r plus h whole square. Okay, this I can write. Now look what we'll do. We'll take, see this G, oh sorry, this is G prime. Since it is at height, this is G prime. Okay, this is G prime. So let us take G prime by G. G we know this is Gm by r square. Okay, so this is Gm by r plus h whole square, and G small g we know this is on the earth surface, so Gm will be here and r square will be on the top. So take the ratio of this two. So we'll write this left hand side as it is, but this will go off, and then see you will write here r square by r plus h whole square. Okay, so now look, if my r is much greater than, h, then we can do such an approximation by expanding it binomially. So look, if I come here, so this, okay, let me clean some portions here. I'm sorry, there is some problem in the pen and writing pad. So then I'll stop it here. Next day maybe I'll just show you the variation of the acceleration due to gravity. So I'll stop it here for today. It is already 3:20, so 5:20. So I'll stop it here. Next day what we'll do, we'll see the variation of acceleration due to gravity with height. And so here simply you have to just do the binomial expansion here. If you take this r square common, so 1 plus h by r will be coming here, and then you can do some approximation. It is very unfortunate we could not do that because of this problem. Okay, anyway, so we'll stop it here for today. We'll meet again on next Tuesday. Next week, Tuesday. On that day, we'll discuss this thing, and we'll take up various numerical problems on the on the basis of this knowledge. Okay. All right. So bye for today.